Okay, so the first thing that we're looking at is the null hypothesis. This is the thing that we're saying is true, either taken at face value or like there's nothing to see here type of deal. So to perform a hypothesis test, we must first translate our question of interest into a statement about our model parameters. So in general, we say our null is our parameter. Our parameter is equal to some sort of hypothesized value. How many people, we think that 60% of the students at DC like null or like block scheduling. The alternate hypothesis, or the H sub A, contains the values of the parameter we consider plausible when we reject the null. How far away are we? Like maybe we want to be above, maybe we think the data is above our null hypothesis. Maybe we think we're below the null hypothesis. The next thing after we come up with our hypothesis is to actually develop the model that we were going to be using. Now I want you to think about proportions. So to plan a statistical hypothesis test, we were going to specify the parameter of interest, that's our P, and the model you will use to test the null hypothesis and parameter. Now when we're talking about model, we basically know only one, which is the normal model. So all models require assumptions, so state the assumptions and check any corresponding conditions. Your model step should end with a statement such as, since the conditions are satisfied, I will model the sampling distribution of the proportion with a normal model, because we are going to use a normal model, and then we'll state out the mean and the standard deviation. In other words, you can continue the hypothesis test. We always check our assumptions and conditions prior to just doing the thing. We never just do the work like a normal math class and then give an answer. We have to justify that our model is sufficiently normal to do what we want to do. So be careful. It is possible that you will not meet the conditions and you'll have to say, since the conditions have not been met, I cannot continue with the test of the model with these methodologies. There are some cases. Maybe you have a convenience sampling. Maybe you just do an internet poll. Those are not simple random samples. We cannot do the things that we like to do. We have those conditions that we know of. So each test we will discuss in the book, and there are a few, has a name that you must include in your report. I don't make the rules. Statisticians and the AP test need these. So the test we will first consider about proportions is called a one proportion Z test. So now I've introduced two names. This is the test we will take. If we were building a confidence interval, we had a one proportion Z interval, if you recall from chapter 19. So now we have a Z interval and a Z test. Both are using the letter Z. When you see Z's, you should think a normal model. The next thing that we do, which are the mechanics, or like do the work. Under our mechanics, we do the actual calculation of our test statistic from the data. So different tests will have different formulas and different test statistics. So for the current cases of proportions, on your calculator, you're going to go stats, tests, and then you're going to go one prop Z test. Or on your TI Inspire, you're going to go menu, statistics, tests, one prop Z test. And then you're going to be given this table of things. And just like we saw with confidence intervals, we're adding a new thing. So P naught, which is our hypothesized value. That's our null hypothesis. We have our X, which is the number of successes. We have N, which is our sample size. And then we have this question that we have to figure out. What is our alternate hypothesis? Are we not equal to? Are we above? Or we're below? So this calculates the probability. This test that I have listed here calculates the probability of obtaining a proportion in a sample from a theorized proportion in the population from which the sample was drawn, aka looking at the sampling distribution given the assumed mean. So real statistics are done on the computer, and you can use the calculator to obtain your test statistic p-value. But you must set up the formula for my tests and the AP test. Again, I don't make the rules, but this is what we are asked to do. Okay, so what is the formula that you have to set up? So the conditions for a 1 proportion z test are the exact same for the 1 proportion z interval, and we should be very familiar with those by now. So we test our hypothesis, or a null hypothesis. We say p is equal to some initial proportion. And then using the statistic, z-scores. What is the proportion of getting the z-value? Well, if you remember, the z-value is just your value minus the mean over the standard deviation. Well, we've done this before, only this time we're saying we're starting, our value is p hat minus the assumed hypothesized proportion divided by the standard error, just like we found. Standard error would be for the hypothesized proportion, p naught q naught over n. When the conditions are met and the null hypothesis is true, this statistic follows the standard normal model, so we can use that model to obtain our p-value. And that's actually what the calculator is using, is we're making a normal model. So the ultimate goal of the calculation is to obtain a p-value and then make a decision based off of that p-value. The p-value, again, is the conditional probability that the observed statistic could occur if the null model were correct. If the p-value is small enough, we will reject the null as simply being too unlikely. If we're 2 or more standard deviations, the probability that we get that is pretty low, which means that it's unusual to get that actual data value. So note, the p-value is a conditional probability, and it's the probability that the observed results could have happened if the null hypothesis was true. So if the null was true and I get a really low probability, then this is unlikely to happen. But lastly, in this process that I've explained to you, is to make your conclusion. And the conclusion in a hypothesis test is a statement about the null hypothesis. So the conclusion must state either one of the two. You do not have a choice in this. Either we reject the null hypothesis or we fail to reject the null hypothesis. Those are your only two choices. Do not write them any other way. Just keep it simple. Do not use flowery language. This is not AP Lit or AP Lang. I just want you to keep it simple. We either reject the null or fail to reject. Finally, we conclude with a sentence interpreting in context what you have found. As always, the conclusion should be stated in context. In other words, answer the question with a complete sentence. Do not simply repeat the decision. So you say, we're going to reject or fail to reject the null, and then what does that mean in context? There was, like this, there was not sufficient evidence to claim the water contained mercury levels greater than 2 parts per million and was not safe to drink. That is a sentence that wraps up what your conclusion is. Okay, so I've kind of walked you through the theoretical lens for making a hypothesis test. So for those needing a little more guidance and like mnemonics, here is another mnemonic. Remember, what I said before about confidence intervals was panic. Panic was parameter, assumptions and conditions, name the test, find the interval, and then we have our conclusion. Now I'm going to say we have phantoms. Surmise what you think about the acronym represents. So like maybe you can already figure out what phantoms mean, but I will spell it out. And then in our next video, we are just going to do some examples. So with phantoms, P stands for define the parameter. H is state the hypothesis. This is giving the null hypothesis. A, check the assumptions and conditions. N, name the test statistic. So for right now, all we have is a 1 prop Z test. T is calculate the test statistic. So that is, in this case, the Z value, or Z-score. O is attain the p-value. What's the probability of getting that Z-score? M is make the decision, reject or fail to reject the null. Those are our 2 and only 2 options. And finally, state your conclusion in context. This is phantoms. Now note, this is not a mnemonic recognized by the AP, so you will get no credit for writing the acronym phantoms. This is intended simply to minimize forgetting part of the process. We've got one extra thing to add, and then we will end the video. So we focused all on this null, and I've described the process to you, and it seems kind of nebulous. I want to quickly turn our attention to the alternate hypothesis. So let's just spend a little time on the alternate hypothesis, HA. We know our null is kind of like this base case, what we're assuming to be true. Well, sometimes we know something about the data that will give us a head start on testing the null hypothesis. Perhaps we're only interested in change in one direction. So for example, a tutor certainly hopes a student's grades improves. She wouldn't necessarily be interested in a reduction of grades. They didn't really do their job if their grades are the same or going down. So thus we conclude that there are three possible alternate hypotheses. Well, we either have the parameter is not equal to the hypothesized value, where we are interested if we are above or below our curve, or we are looking at our curve and we're seeing, are we just below this? Or we're looking at our curve and we're saying, are we above this? So we could be less than our hypothesized value, or we can be greater than our hypothesized value. All three of those are equivalent. Now, just to get into the context of this, if we say we're not equal to, or if our alternate hypothesis is our parameter is not equal to our hypothesis test, this is called a two-tailed test because we are equally interested in the deviations on either side of the null hypothesis. Usually that is because we have no idea which way things are going. So for a two-tailed alternate hypothesis, the p-value is the probability of deviating in either direction. So if I say that my alpha level, the level that I want to be convinced that the p-value is small enough, is 0.16, and I say that my alternate is we're not equal to, I care above or below my curve. Well, I want the total to be 0.16, so I'm either 0.08 below or 0.08 above. Note that that's half of my alpha level on either side. So the p-value is the total probability sufficient for us to reject the null. And if I don't know which direction I'm going, I have to half it on either side because it could be equally as likely. Now, for less than or greater than, the two alternate hypotheses are called one-tailed alternate hypothesis tests. A one-tailed alternate focuses on deviations from the null hypothesis only one direction. Perhaps we know the deviations can only be in one direction, or the deviations are only acceptable in one direction. Thus, the p-value for one-sided alternatives is the probability of deviating only in that direction away from the null. For example, if I want to be below my predetermined value with an alpha level of 0.08, then my cut value is just 0.08. Notice it's not doubled. Or if I want to be above 0.08, I just go 0.08. And lastly, p-values and decisions. How small should the p-value be for you to reject the null hypothesis? Well, the primary consideration when evaluating the p-value is that the decision is done before, a priori. The choice of the alpha is made before you go about collecting the data. You don't make the alpha level fit your data. So that decision is usually up to the researcher. I'll generally tell you what it is, and is primarily influenced by context and tradition. A long-standing historical, generally accepted hypothesis believed by many to be true, i.e. is accepted by the majority of experts with much precedent, needs stronger evidence and thus a small p-value to reject the null. Another factor in choosing alpha is the importance or the value of the parameter being tested. Like, think about this. If you're screening for a disease and want to be sure we treat all of those who are ill, we may be willing to reject the null hypothesis of no disease with a fairly large p-value. We're okay if we make a little bit of error because we want to make sure people are healthy. However, the flip side is the side effects of a treatment. If the side effects of a treatment are significant and severe, we may choose to only reject the null of no disease with a much smaller p-value. So if we're trying a cancer treatment and we want to make sure that I know it gets got really bad side effects, that it works, I want to be really certain. So I want a low alpha level. So your conclusions about any null hypothesis must include the p-value of your test. You must always support your contentions with data. This is what this class is about. You got to support your work with data. If you do reject the null, when possible, it is good policy to include a confidence interval for the parameter of interest. Now, I just said that really fast, but it's good practice that if you reject the null, if you reject the null, that you also build a confidence interval of where it could be. So what does that mean is you've rejected the model represented by null, so we're going to provide an alternate solution. Don't just declare the null hypothesis rejected or not rejected. You're going to report the p-value and the test statistic to show the strength of evidence against the null hypothesis. This will let your audience know the conditions for rejecting or failing to reject the null. So if you've been paying attention, you may have noticed that the process of hypothesis tests involves much of the same concepts as determining confidence intervals. Hypothesis testing and confidence intervals are actually related. So the confidence interval starts with a statistic. Remember, we said this was p hat, and hypothesized a possible range of values for the parameter, the true population proportion. This was our confidence interval. Hypothesis testing begins with a parameter and, using the same techniques determined in confidence intervals, tests a statistic against that parameter and saying, is this statistic plausible? Hypothesis testing builds an interval around a parameter and tests to see if the statistics falls within that interval. So again, on your calculator, we're going to go stats tests 1 prop z-test. Our calculator is going to report out the hypothesis test, the z-score, this is our test statistic, this is our p-value, this is our sample proportion, and this is our sample size. I think this is everything we need to actually do the work. Now, I want you to think through this process because this is new. So next video, we are going to do 1, if not 2 examples with the calculator and everything. So thank you for listening, Falcons. I will see you in the next one.